Hello everyone and welcome back to the channel. I'm Lena, an AI consultant working as a freelancer in partnership with Weymont Digital Marketing Company. In today's video, we're going to break down some core concepts of vector databases, explained in simple, easy-to-follow language so that anyone, whether you're a student, an IT professional, or an aspiring entrepreneur, can understand how this exciting technology works. By the end of this video, you'll clearly understand what embeddings and vector representations are, how text, images, and audio are converted into embeddings, what similarity measures mean and why they matter, how indexing and searching work in a vector database, and the role of metadata and hybrid search in improving results. So, let's dive right in. Understanding embeddings and vector representation. What does these mean? Let's start with a simple question. What are embeddings and what does vector representation really mean? Imagine you're describing the word apple. To humans, that means a fruit round, sweet, maybe red or green. But computers don't understand words or images the way we do. They need numbers to represent meaning. So, in the world of AI, every word, image, or sound is converted into a list of numbers called a vector. Each vector is like a map that describes the meaning or features of that object in a multi-dimensional space. Here's an example. Let's take the same example which Ben explained in our previous video on vector database. Let's say the word king is represented by 0.25, 0.78, 0.65. And queen might be 0.26, 0.79, 0.64. Notice how similar the numbers are. That's because their meanings are close, both represent royalty. But the word apple might be something like 0.90, 0.12, 0.05, which is completely different because its meaning is far away in that space. So, embeddings help the computer understand meaning, not just exact words. That's why when you search for mobile phone, it can also find smartphone or cell phone because their vectors are similar. To summarize, embeddings mean numerical meaning of data. Vectors mean lists of numbers representing that meaning. Vector space mean the world where all these meanings live and can be compared. These are the basic concept of embeddings and vector database. Hope you are clear with the context. Now that we know what embeddings are, let's see how they're created from text, images, and audio. How text, images, and audio are converted into embeddings. Let's talk about text embeddings first. For text, AI models like OpenAI's embedding models, or BERT, take words, sentences, or even paragraphs and convert them into vectors. Each number in the vector captures a small piece of meaning such as emotion, topic, or intent. For example, I love coffee. This phrase might turn into a vector like 0.21, 0.75, 0.12, 0.89. The model learns from millions of examples so that similar phrases like I enjoy espresso end up having close vector values. So, when we store both in a vector database, the system can easily find connections between love coffee and enjoy espresso, even if the exact words differ. Hope you are clear with text embeddings. Now let's talk about image embeddings. The images embeddings work the same way as text embeddings. An image model like Clip or ResNet looks at patterns, colors, shapes, objects, and converts them into a vector. For instance, a photo of a cat might be represented as 0.45, 0.67, 0.11, 0.33. Another photo of a kitten would produce a vector very close to that, because the model recognizes they're visually similar. I believe you have understood about text and image embeddings. Now let's talk about audio embeddings. Audio models like Whisper or WAV2Vec analyze sounds, pitch, rhythm, and speech to form embeddings. For instance, the word hello, spoken by two people in different tones, might still produce very similar vectors, meaning the computer understands they both represent the same idea. So, embeddings act as a bridge between human understanding and machine understanding, turning everything, text, image, audio, into numbers that carry meaning. Trust you are clear with the embeddings and the models used in each embeddings. So the concept is same, but the models are different for each embeddings. Let's move on to next concept called similarity measures. This is one of the core concepts in vector database. Assume that our data is in vector form, How do we find which ones are similar? Let's say we have a database full of embeddings, thousands or even millions. You type a query, for example, cute cats. The system will convert your query into a vector and then compare it with all the vectors in the database to find the closest match. But how does the system know which ones are close? That's where similarity measures come in. These are mathematical methods used to compare two vectors. Let's look at the three most common ones: cosine, Euclidean, dot product. I am pretty sure that you might have learned in your school or college days. Do you? If not, no worries, we will do the quick recap one by one. The first one is cosine similarity. Think of vectors as arrows pointing in space. Cosine similarity measures the angle between two vectors. If the angle is small, meaning they point in almost the same direction, they're similar. If the angle is large, they're different. This method is great for text because it focuses on meaning, not size. The next one is Euclidean distance. This one measures the actual distance between two vectors, like measuring how far 2 points are apart on a map. The smaller the distance, the more similar they are. This method is often used in image or audio search, where exact patterns matter. The last one is dot product. The dot product calculates similarity based on how much two vectors align with each other. It's commonly used in deep learning models because it's simple and fast for large-scale comparisons. So, when you search for something, your query vector is compared using one of these methods, and the database returns the vectors, or results that are most similar. That's how vector search feels so smart. It's not just keyword matching, it understands the meaning. Hope you are clear. Now let's talk about what makes vector databases special indexing and searching efficiently. For instance, when we have millions of embeddings, it's not practical to compare every single one during a search that would be too slow. So, vector databases use something called indexing to organize and group similar vectors together. So what is indexing? Indexing is like building a smart structure, a kind of map, that helps the database quickly locate the most relevant vectors without scanning everything. Popular indexing techniques include HNSW, IVF, and PQ. Let's understand what each indexing do in vector database. First, HNSW, which is Hierarchical Navigable Small World Graph. A graph-based method that links similar vectors together, making searches very fast. Second, IVF, which is Inverted File Index. It divides vectors into clusters or buckets, so searches happen only in the most relevant areas. Third, PQYHC is product quantization. It compresses data so it can search large datasets with minimal memory use. Now let's talk about how the search works. When a query comes in, the database converts it into a vector, then uses the index to jump directly to the area where similar vectors are likely to be found. Afterwards, it measures similarity using cosine or Euclidean distance. Then it returns the top results, usually in milliseconds. This is how tools like Pinecone, Weaviate, Milvus, or FICE power fast semantic search in modern AI systems. So, indexing is the secret sauce that makes vector databases both smart and lightning fast. Hope you understand the logic behind the process of search works. Before we wrap up, let's talk about two more important concepts: metadata and hybrid search. What is metadata? Let me add the context here. While vectors capture meaning, they don't store extra details like date, author, file type, or category. That's where metadata comes in. Metadata is like the label or description attached to your data. For example, if you have an image vector for a cat photo, metadata might include: file name is cat1.jpg. Category is animals. Date uploaded is October 2025. So when you search, you can filter results by metadata, like only show images from October 2025, making your search more accurate and meaningful. Now let's talk about hybrid search. The best of both worlds. Hybrid search combines traditional keyword search with vector-based semantic search. Why? Because sometimes we need both precision and meaning. For example, if you search for Tesla Model 3 specifications. What happens is, the keyword search ensures the exact term Model 3 is found. The vector search brings in semantically similar results like Tesla 3 specs or features of Model 3 car. This approach gives you richer, more relevant search results, especially in business or e-commerce applications where context and accuracy both matter. So we have covered very important topics today. I hope you have got the basic understanding of each topic dissected so far. Now, let's recap what we learned today. First, embeddings represent meaning as numbers, allowing computers to understand human language and visuals. Second, text, images, and audio can all be turned into embeddings using AI models. Third, similarity measures like cosine, Euclidean, and dot product help find related results. Fourth, indexing makes vector search fast and efficient, even with millions of data points. Fifth, metadata and hybrid search bring structure and context to improve the overall search experience. The vector databases are the backbone of modern AI applications, from recommendation systems and chatbots to search engines and voice assistants. So if you want to understand how tools like ChatGPT, Google Lens, or Spotify recommendations actually work, it all starts here, with vectors and embeddings. Thank you for watching. If you found this video useful, please remember to like, subscribe, and share it with your friends. We'll soon be releasing more such videos on AI, machine learning, and vector databases. So stay tuned and keep growing your knowledge with us. Until then, take care and keep exploring the exciting world of AI. Thank you once again.